All right, let's dive deep into the world of electric currents and resistance, of course. You sent over a chapter from a physics textbook. It's LIF 103 compressed.pdf, along with, oh, some practice problems too, so we know you're serious about this.
Always love to see it.
Right. So have you ever, like, stopped to think about what's really happening? At the atomic level, I mean. When, you charge your phone or flip on a light.
It's more than meets the eye, that's for sure.
It's way more interesting than people think. One thing that blew my mind was, like, those electrons, the ones we always hear about, they aren't actually racing through wires super fast.
Yeah, it's a common misconception.
It is. It's more like, imagine a slow-moving crowd, but like a huge crowd. And that's what creates the current. Wild, right?
Huge numbers, tiny particles, that's the key.
And then there's this whole thing about how the resistance of a metal, it can actually change with temperature.
Oh yeah, that's a big one. Gets into the nitty-gritty of how materials behave.
Definitely. Okay, so the textbook actually emphasizes this idea of net charge flow when it defines electric current, which is in section 3.2.
Right, and that's important because it's not just electrons moving in one direction.
Oh, okay, I see what you get at. So it's not as simple as, like, electrons marching in a straight line.
Not quite. Both positive and negative charges can contribute to the overall current.
Huh, interesting.
It's more like, think of a busy street, right, with people walking in both directions.
Okay, yeah.
Even if some people are, moving back and forth, the overall flow of the crowd, that's what determines the current.
So it's like the overall movement of the crowd is what matters, not just each individual person.
Exactly. And that net movement of charge, that's what we call electric current.
Gotcha. Okay, now let's talk about those, slow-moving electrons. The textbook uses this term drift velocity. There's even an example, it's in section 3.2, showing that electrons in a copper wire, they only move like a few millimeters per second.
Yeah, it's surprisingly slow.
It seems way too slow for something that feels so instantaneous.
Right, but think about it like this. You've got this single electron, right? And it's trying to make its way through this dense forest of atoms in the wire.
Okay, I can picture that.
And it's constantly bumping into them, which slows it down. So drift velocity is basically the average speed of the electrons as they're moving through a conductor.
So they're not, like, zipping through the wires, but it's their collective movement that creates the current we actually see.
Exactly. Think of a packed highway, rush hour. Cars are moving slowly, but there are so many of them. That overall flow of traffic, still significant. Same idea.
Oh, that's a good way to put it. Okay, so then how come, if the electrons are moving that slowly, why do lights turn on right away when you flip the switch? Shouldn't there be, like, a delay?
That's a great question, and the answer lies in understanding the electric field. See, when you close a circuit, the electric field, it's established almost instantly throughout the whole wire,
Oh, okay.
like a chain reaction. And it's this field that sets all the electrons in motion at basically the same time, even though, yeah, their individual movement is slow.
So the electric field is like the signal, traveling through the wire super fast, and that's why we don't notice a delay. Like a domino effect, kind of.
You got it. The speed of that electric field, that's what makes things seem instant, not the speed of each electron on its own.
Okay, that makes a lot more sense now. So then there's Ohm's law. The textbook talks about that in section 3.4, describes it as this, like, fundamental relationship between voltage, current, and resistance.
The trifecta.
Right, and the formula is VEIR, right?
That's the one. Ohm's law is basically like a recipe. It links these three crucial electrical quantities, tells us the voltage, which is like the driving force behind the current, is directly proportional to the current itself.
Okay.
And the resistance of the material, that acts like a proportionality constant. It influences how much current's going to flow for a given voltage.
So if you up the voltage, you get more current. But if you up the resistance, you get less current.
Exactly. It's a balancing act.
Got to keep things in check.
And this balance, that's what makes electrical circuits actually work. But it's worth noting, Ohm's law is a simplification. Doesn't always hold true in every situation.
Oh, really? I was going to say it seemed almost too simple. The textbook does mention some limitations of Ohm's law. It's in section 3.6. So are there cases where it just doesn't apply?
Yeah, definitely. Like some materials, they just don't behave linearly. Their resistance changes depending on the voltage. Diodes are a good example.
So it's not always the straightforward relationship between voltage, current, and resistance.
Exactly. Ohm's law is a good model, works well for a lot of common materials, but it's still a model, right?
Right. Models have their limits.
They do. Speaking of resistance, though, the textbook also talks about internal resistance.
Yeah, I saw that. Section 3.10, that's the resistance inside the power source itself, like a battery.
Exactly.
Why does that matter?
Well, think of it this way. Internal resistance basically limits how much current the power source can actually deliver. It's like, imagine a bottleneck in a pipe.
Oh, okay.
Even if you've got like a ton of pressure behind the water, that bottleneck restricts how much can actually flow through.
So a battery with higher internal resistance, it can't deliver as much current, even if it has a high voltage.
That's it. It's one of the reasons why, like, a car battery, which is meant to deliver a huge surge of current, right, to start the engine,
Right.
it's so much bigger than, say, a tiny watch battery.
Oh, interesting. So it's not just the size of the battery, but also the internal resistance.
Absolutely. It's a key factor to think about when you're designing circuits, or just using them.
Makes sense. Okay, now what about dot resistivity? The textbook defines that in section 3.7, talks about how much a material resists the flow of current. And it mentions that resistivity can be wildly different between different materials.
Oh, for sure. Resistivity is an intrinsic property, like copper, which is used in wiring all the time. It's got very low resistivity, meaning current flows through it easily.
Okay.
But then you've got something like rubber, which is used as an insulator, that's got extremely high resistivity, so it basically blocks current.
That's why we use copper for wires and rubber to cover them, to make them safe to touch.
Exactly. Huge difference in resistivity. And what's even more interesting is the resistivity of a material can change with temperature.
Oh, really? How so?
Well, for most metals, the resistivity goes up as the temperature increases.
Why is that?
Think about those electrons again, trying to move through the wire.
Okay.
As the temperature goes up, the atoms in the wire, they start vibrating more, more vigorously. Makes it harder for the electrons to get through.
So it's like more obstacles in their way.
Exactly. More atomic vibrations, more resistance. But there are exceptions. Some materials, like nichrome, that's used a lot in heating elements.
Okay.
Their resistivity stays pretty stable even at high temperatures. That's why they're good for things like, toasters, hair dryers, where you need that consistent resistance to make heat.
So it's all about using the right material for the job.
Right. Different properties for different applications. Now, have you ever heard of semiconductors?
Yeah, they're kind of like in between a conductor and an insulator, right?
Exactly. And their behavior is really interesting because their resistivity actually decreases as the temperature goes up.
Wait, really? That seems counterintuitive.
It is, but it's because of how the charge carriers behave in semiconductors. Unlike metals, where the number of free electrons stays pretty constant, the number of charge carriers in a semiconductor, it actually increases with temperature.
So as it gets hotter, there are more charge carrier.
More to carry the current. And that outweighs the effect of, those increased atomic vibrations.
So it's like even if there's more traffic, the overall flow is better because there are more lanes open.
Perfect analogy. That's why semiconductors are so versatile, used in tons of electronic devices.
Makes sense. Okay, what about power? Section 3.9 defines it as the rate at which energy is used, measured in watts, and the formula is PEIV, right?
Yep, that's the basic one.
But there are also those other versions, like PE I2R and PEV2R. Why so many?
They're all equivalent, really, just highlight different relationships between the voltage, current, and resistance. It's about having options, for solving problems.
So depending on what you know, you can pick the easiest formula to use.
Exactly. Like if you know the current and the resistance, use PEV-I2R. If you know the voltage and the resistance, maybe PEV2R is easier.
Makes sense, like having different ways to get to the same place. Okay, now the textbook also goes into cells. In section 3.10, talks about them being like the building blocks of batteries, and it uses this term electromotive force, or EMF.
Sounds kind of scary, right?
Yeah, a little bit. What is that exactly?
It's a bit of a misnomer, actually. Not really a force. It's more like the electrical pressure that drives the current, the energy the cell provides per unit charge.
So it's the potential difference that gets the charges moving.
Exactly. And just like any power source, cells have internal resistance, which, as we talked about, limits the current.
Right, right. Even the best battery has some internal resistance.
Yep. Now, things get even more interesting when you start combining cells, like in series or in parallel.
Oh yeah, the textbook talks about that. Section 3.11, what happens when you do that?
Well, connecting them in series is like stacking blocks. Each cell adds its voltage to the total, like adding more batteries to a flashlight to make it brighter, but you're also adding the internal resistances, so you might limit the current a bit.
A trade-off. More voltage, but maybe less current.
Exactly. Now, connecting them in parallel, it's like creating multiple paths for the current to flow.
So instead of more voltage, you get more capacity to deliver current.
Right. Total voltage stays the same, but the combined internal resistance goes down.
Like a team of workers sharing a task, each one has their limit, but together they can handle a lot more.
Exactly. Gives you a lot of flexibility when you're designing circuits for different needs.
Okay, so we've covered a lot here. It's pretty amazing how, these seemingly basic concepts end up creating these really complex systems.
It is, yeah. Electricity is all around us, but most people don't think about what's going on beneath the surface.
Right. The textbook actually has a point to ponder at the end, and it's a really good one. It asks, if all materials deviate from Ohm's law under extreme conditions, what does that tell us about the limits of models in physics?
Ooh, that's a deep one. What do you think? It really make you think, huh? About how we model things in physics. like Ohm's law. It's great, works well in a lot of situations,
Right.
but push things far enough to extremes, it breaks down. Every material does, actually.
So it's like, okay, imagine you've got a map, right? And it's perfect for navigating a city, streets, landmarks, everything.
Right.
But then you try to use that same map to like explore a huge uncharted wilderness.
Yeah, not going to be so useful. Might even lead you astray.
Exactly. And that's kind of what that point to ponder is getting at.
Totally. Models in physics, they give us this framework, right, for understanding things that are really complex,
Right.
but they're not like perfect replicas of reality.
Right. They have their limits.
They do. And recognizing those limits is super important.
Makes you think about critical thinking in science, too. Can't just blindly accept a model as like the absolute truth.
Oh, for sure. Got to be aware of those limitations. And, always be ready to refine things as our understanding evolves.
Science is a journey, not a destination. Right.
Well said. Models are the tools that help us along the way. But we got to remember, they're just tools. Could always need some tweaking or even a complete overhaul.
That's a good way to put it. Well, this has been an awesome deep dive. I feel like we've really uncovered some hidden complexities here.
We did, yeah. Went from basic circuits to, questioning the very models we use in physics.
It's been a wild ride. And to our listener, thank you so much for joining us on this electrifying journey. We hope you learned something new, maybe even got inspired to, explore some of those practice problems the textbook has.
Yeah, give them a shot. See what you can figure out.
Keep those brain circuits firing, and until next time, happy exploring. 6EA.